Presentation visible?
Yes, sir.
Okay, good. So we have been discussing about the semantics of lambda expression. And let me just quickly recap what we have done before we proceed, because this is a part which is going to be very, very important in terms of the uh, subsequent topics that we will discuss, whether it is type system or denotational semantics and so on. So the first thing we talked about was, let me come straight to slide 14. The first thing we all know by now that every lambda expression may have a set of free variables and a set of bound variables. Bound variables are those which have the lambda as the binder, and a free variable is one which does not have any binder. So the free variable will, for the actual evaluation of the expression, as we'll see subsequently, the free variables will need to be set from the environment. So these are like, in a loose way, these are equivalent of global for a C function, and bound variables are those which come as parameters or local variables. So the first thing we discussed was to compute the set of free variables for an expression, which is done through this recursive algorithm. So for a constant, the set of free variables is empty. For a variable, it is a set containing that variable, of course. If we have a function application combination, then the set of free variables is a union of the set of free variables in the both the writer and the rand. And in a lambda abstraction, the set of free variables is a set of free variables in the function body, from which we have to take away the variable which is bound by the binder, which is x here, right? And any lambda expression which has an empty set of free variables is called closed, right? So this is the basic building block. And then the rule for actually evaluating a lambda expression or giving meaning to a lambda expression is to do a substitution, is to try to, make it simpler by performing all the function applications that are possible. So this is done by a process of substitution, where we introduced a notation for substitution, which refers to the lambda expression, which is obtained by each free occurrence of V in E1. V by E1 in the expression E, right? That is the substitution. So if V is any variable, then it gives E1. If V is if it is applied on X, where X is not same as V, then it is X, and the other two are similarly defined. And with this, we observe that these rules, these four rules of substitution that we form, are actually not sound, because they will lead to a number of possible unsafe substitutions. That is, substitution which changes the meaning of the lambda expression, particularly by two possibilities. One possibility is that in this substitution rule, we are not specifically checking if the variable being substituted is free or not. So substitution has to happen for free variables only. It cannot happen for a bound variable, because in that case, it basically becomes equivalent of doing a function application. It is not a substitution. So that we have seen that unless we take care of the freeness of the variable, then we will have unsafe substitution, which will be wrong substitution. And the second case that we have seen is what we'll have to specifically note in terms of the names of variables, that after the substitution or during the substitution, we should not have a name clash or a variable capture, which is defined by the fact that if a variable is originally free, then after substitution, it should not become bound. So that is what we see here in the lambda expression on top, that y is actually free. But since we are substituting y by x, which is bound, in the resulting expression, the variable x here gets bound. The substituted variable x gets bound, which naturally changes the meaning of the expression. So for this is what is called the name clash. And to avoid that, we have given the method, we have taken the method that we can simply do this by doing a renaming of variables. That is, rename it to something different. You can, any bound variable, you can name it to anything else. It does not really matter. It's like the formal parameter of a C function can be, the name of the formal parameter of a C function can be consistently changed without changing any meaning or computation of the function. So in that way, we since x is going to get captured by this substitution, so before the substitution, we first change that x to some other variable here z, which is not same as which does not occur in the expressions at all. And after that, we go ahead and do substitution. So these are the two factors. One is that substitution has to happen in terms of the free variables, and the other is there should not be any variable capture, are the two factors which has to be brought into the substitution rule. So with those, we have now 7 rules. The first is the simple. For any variable, if you substitute it by an expression, you get the expression. For any variable other than the variable you are substituting, if you try a substitution, then you have that original variable itself. Constant certainly does not change. If you have a function application, then the substitution applies each to the retur and rand, and then the application will happen. But actual changes take place in terms of the function abstraction, where we have to see that if V is not free in E, then we cannot do the substitution. Actually, substitution will have no effect because we cannot substitute that. In other case, if we have that V is actually free, then we can do the substitution by substituting V in the body of the function abstraction. Okay? And we have to make sure that X is not free in E1. Okay? And the third is when the when we have the case, this is these two, 5 and 6, take care of the issue of the variable being free. This rule 7 basically tells about the name capture, variable capture, or the name clash. So if we have a substitution such that it is possible that after the substitution, the variable in E1 might get captured, then we can always do a renaming. So we first do a substitution for renaming, and then we go ahead and do the actual substitution, what we wanted to do. Right? So these are the 7 rules. And with that, in slide 20, we saw a basic process of substitution of a given expression. And twice we had to actually do use rule 7, which means that we had to do the renaming in that. So equipped with that, we actually talk about the semantics of lambda expression, which is called reduction. So a lambda expression has its meaning as another lambda expression that result after all function applications are carried out, right? So this is unique in lambda calculus, is unique in the way that its semantic is actually expressed by the language itself. And this process is called the reduction process. And we have 4 rules, but primarily the primary rule for reduction is the beta reduction rule, which is the substitution rule that we have just seen. And to support that, we have the renaming rule. Then we have 2 other auxiliary rules. So the alpha reduction or renaming, as we have just seen, we are formally writing it here in terms of the alpha reduction. It is just, replacing consistently the variable v by variable w in all occurrences in E, right? So obviously you have to make sure that the w does not occur in E before that, because in that case you will have another name clash arising from there, right? And we also observe that this direction of reduction is a process that we follow, but in terms of semantics, actually the lambda expression on both sides of this reduction are actually equivalent. So they are congruent expressions, and we can, this is the earlier. So we can actually, take the, just consider them equivalent expression, congruent expression. The direction is just for the process of reduction. And then we have beta reduction, which is the main rule of lambda semantics, where we substitute v, the bound variable here, that by v by E1, right? So for that, what we need is in E. So this is the evaluation of function application. The function is lambda v dot E, and you are applying it on E1. So what we need to do is to substitute v by E1. And it has to be a self-substitution, which means that in E, all occurrences of v must be free, right? Mind you, this is, just be careful that in lambda v dot E, v is bound. But when we take E itself, v has to be free in E for this substitution by E1 to be safe. So this is the process of beta reduction, and which is basically what, in simple terms, what it means. It's a function evaluation. It's a function application. It is a function invocation, as we know in common programming languages. Okay? So the left-hand side is of the beta reduction is called a beta redex, which means that there is a possibility of evaluating a function, doing a function application. And we will continue to do this in an expression as long as beta redexes exist. And of course, in terms of doing the beta reduction, if we see a possibility of name clash, then we'll use alpha reduction to make the substitution valid. Again, the 2 sides of the beta reduction are actually congruent, and they can be seen in both directions. And it is simple to see that they are reflexive and transitive. So we can say that the entire process of lambda reduction is basically a repeated application of the beta reduction or alpha reduction, as the case may be. So that is a transitive, reflexive transitive closure that we are referring to here. The term beta abstraction is just the reverse of reduction. So if you change the sides of the reduction, then you call it an abstraction. So you have the evaluated function, and from that you are going back to the function application lambda. So that is called an abstraction rule, because the earlier one was making it more concrete because you are evaluating. This one is making it more abstract, and these two rules together is called beta conversion. So you can say that again, the two expressions are both ways convertible, and they are equivalent, and naturally the reflexive transitive closure of that holds in terms of the lambda calculus. Then comes alpha reduction. Alpha reduction basically talks about when you have two lambda expressions which basically mean the same function. Right? So I'm very sorry. The eta reduction, not alpha. The eta reduction basically denotes that you have two functions and these two functions are same. Okay? So here, if we have lambda v dot e applied onto v, if this is same as e, then we say that we are doing a eta reduction. So lambda x square x is basically the function square, or lambda x dot add 5x, add takes naturally two parameters, is add 5, right? Where add 5 is basically the carried version of the function add. Right? So in general terms, we can certainly say that two functions are same if for all arguments they produce the same result. Right? So then these two functions are same, and eta reduction makes use of that. So eta reduction at times just helps you to simplify things, and oftentimes eta reduction will be useful when we have some functions from the domain. Okay. And finally, we have the delta reduction rule, where the properties of the constant functions of the domain, predefined constants, and the constant functions of the domain, the properties of them can be taken care of. So add 3, 5 as a lambda expression is a reduced expression unless you know that 3 and 5 are numerals and add is a binary function on numerals, and it has the property that taking 3 and 5, it can produce another numeral constant 8, and so on. So we can do this reduction provided we know these properties of the domain. Similarly, a lambda expression not true will mean a lambda expression false, provided we use the properties of the Boolean algebra domain and so on. Right? So here is so that is the delta reduction. So eta and delta reductions basically help you simplify things in terms of the certain domain knowledge and function equivalence. But the primary rule of reduction is the beta reduction, which will occasionally make use of the alpha reduction to avoid name clash. So this is what we did, and this is I just did a relatively elaborate recap, because this is very, very important in terms of the understanding of lambda calculus. So let me pause here once and see if you have any questions. Otherwise, I'll move on to the. So is it clear, friends? The basic notion of evaluation, lambda reduction, or the semantics of lambda expressions, the basic 4 rules. If you try to understand them from the simple, meaning of lambda expressions, then there is nothing actually to memorize or remember in this, because the simple thing is that for a substitution, the variable to be substituted must be free, which is quite understandable. And the second is, after the substitution, a variable which was free must not get bound, because that will certainly change the meaning of the whole thing. Rest of the entire rules and so on are just formalizations of whatever is being said in English here. So that gives rise to the beta reduction rule. And our whole task would be to, remove the beta reduxes from a lambda expression and keep on making it simpler and simpler till we are left with no beta redux. That is, no function application is available in that lambda expression. Right? So, any questions? No questions. Good. So let me continue. Now, the point is, in a given a lambda expression, there could be several ways in which it can be evaluated. This is true for our functions also, but we kind of intuitively got adjusted to using functions in a certain way. And we don't question that, because the order of evaluation in case of C function or C++ function and so on are defined for the specific syntax we use for writing that function, or rather writing that callable entity. But just to remind you, it is actually that a function evaluation has multiple different strategies available, and we make use of one strategy or the other depending on the requirement or depending on the properties of the language and so on. So let me remind you of 4 major evaluation strategies that have been followed in languages for a very, very long time. The first, which is possibly the most common, is call by value. And call by value, we understand, is available in C. Almost everything in C is call by value except for arrays. And it's available in C++, most of the other languages, which say that you first evaluate the arguments, the actual parameters of the function to be called. And after evaluation, the resulting value be copied to the formal parameters. That is done typically in a new memory region. So your original variable of the original expression is not touched. It only its value is taken. And that is the value taken by the formal parameters. And with that value, the function goes ahead and does the computation. This is call by value, all of us understand. C++ introduced in C what is known by call by reference. That is, it has a reference type, which is basically an alias of a variable. Or the reference could be constant also, and be a reference or alias of an expression being evaluated. So in call by reference, it does not copy the value of the variable, rather uses an alias of the variable actual parameter as the formal parameter. So the formal parameter, it becomes an alias of the actual parameter. So any changes that are done by in the formal parameter will also be applicable to the actual parameter, right? Now, this is what was introduced in C++. So you can see that call by value typically in programming, common programming language terms, call by value is an input parameter, whereas call by reference is an in-out parameter, input parameter as well as output parameter, because changes do reflect back in the original actual parameter. Now, in C, since reference is not there in C, what we do is we kind of simulate this call by reference in C using call by value by explicitly creating reference such as pointer. Right? So what we do is we write the function not in terms of the formal parameters we need, but in terms of pointers to the formal parameters that we need. And while we pass the actual parameter, instead of passing the variable, we pass the address of that variable. Okay? So what actually gets passed is the pointer, which is by value, because you are just copying that address. But the effect that it produces is that when you use that pointer in the function to make changes in the pointed value, those changes actually happen on the actual parameter also, because it's necessarily the same memory location. And this is to distinguish it from call by reference. This is known as call by address, or CBA. There is a very old mechanism. I mean, just for completeness, I don't think any language has this anymore, which is called call by copy restore. Call by copy restore. Actually, Fortran, when it started, Fortran was the first commonly used imperative programming language. So Fortran, when it started, it had this mechanism, which was subsequently deprecated. What is done is the call part of it is same as call by value. That is, you take the actual parameter and copy it into the formal parameter. Right? So actual parameter remains same. But at the end of the call, you copy back the formal parameter onto the actual parameter. So that is why you say call by copy restore. So that is the restoration, that you had made a copy of the actual parameter. But after the call, you copy the formal parameter back into the actual parameter. It is also known as copy in, copy out mechanism. So you're copying in and you're copying out. So that is how Fortran used to, create, in-out parameters in those days. And it is very, very risky. We will soon see. The fourth, which is very important, is call by name, which is not available in the function mechanism, but in terms of the callable entities of C, C++, it is available as a macro. So in function, what you are doing, you first evaluate the parameters and then pass them to the function, whether by value or by reference, whatever. But in terms of call by name, you pass the parameter expression as it is to the function and substitute them directly in the function body. Okay? So it is different. So you are here. So in call by value, the evaluation, or call by reference, the evaluation of the parameters happen first. The function evaluation happen next. Here, in call by name, the function evaluation is happening first, and the parameter evaluation will happen next because you are substituting the parameters in the function body. So that is the reason this is typically called lazy evaluation. So call by value you all often referred to as eager evaluation. I mean, you are very eager to evaluate, so you first evaluate the expressions. And this is a lazy evaluation. So, okay, we will evaluate the parameters at a later point of time. Let us first evaluate the function. So this is called as a lazy evaluation function. And so lazy evaluation also is very, very useful, particularly for in the context of lambda calculus, available as macros in C, C++. And it has a lot of advantages. It has some disadvantages as well. And there is a variant of this lazy evaluation or call by name, which is known as call by need, where which is a variant of the lazy evaluation in the sense that in case you need to, evaluate the argument multiple times in the call by name, then after the first evaluation, you could memorize a temporary copy, and for the second and third cases of argument evaluation, you could use that subsequently, which is called call by need. Let's hold on that. So this first four, let me try to show you in terms of a simple C++ function example. Right? So I have defined three functions and one macro. Right? So the first one is a function f which takes two parameters, as you can see, by value, changes both of them and returns. So this is what where call by value mechanism is in place. Function g takes the two parameters by reference, makes the same changes. This is obviously call by reference. Call by address, what typically C programmers would have to use, is a function h which takes the two parameters now as pointers to them, pointed to a integer, and then dereferences and does the same computation. So the changes will be seen. So this is called by address. And we have a macro which does a simple multiplication call by name. Right? So let us see if we evaluate what will happen on this. Right? I'm stepping aside and bringing you examples from your known programming language so that we can really see, what in terms of evaluation, what exactly the lambdas would be doing. So please try to understand this clearly, even though I know all of you know this. So we have three variables, x, y, z initialized. If we call fxy, this one, a is incremented, b is decremented, and then it's returned. So if we print xy after the call to fxy, we will get the same value of x and y because these are call by value. So naturally, the value 3 and value 4 were copied into a and b. X and y are not touched. So there is no change. These are call by value property. G has call by reference. So when you call G, x and a becomes an alias of x, b becomes an alias of y. So as you increment a, x actually gets incremented. Similarly, as you decrement b, y actually gets decremented. So x, which was 3, becomes 4. Y, which was 4, becomes 3. Right? In-out parameter, which is call by reference. In H, you are passing now the addresses of x and y, right? Call by address. And at this point, x is 4, y is 3. You have passed the addresses. You are dereferencing that address and then incrementing. So the address of x is dereferenced. here. So actually what you have, this is actually the variable x, you increment that. So from 4, it becomes 5. Similar thing happens for y. You decrement it. So it was 3, it becomes 2. Right? So these three mechanisms between C and C++ are very well understood. To demonstrate call by copy restore, naturally we have to do some imagination, because languages do not support this anymore. So let us see how it would be, and let me show you what the difficulty would be. Let's take this function g, which takes both parameters as reference. Right? So I can actually pass the same parameter z to it. Right? What happens if I pass z to both? There are two aliases of z in this function. A is an alias of z, b is also an alias of z. So when I increment a, z, which was 5, becomes 6. When I decrement b, which is also an alias of z, the z, which had become 6, now becomes 5 again. So if we just run it, execute it, you will get the result as 5. Right? Into once incremented, consistent. Think about it. If I did call by copy restore, so I copy the value of z onto a, it is 5. I copy the value of z onto b, it is 5. A is incremented, becomes 6. B is decremented, becomes 4. Up to this point, there's nothing. Then the point is the copy restore. When the restore happens, the value of this parameter will be copied back to the z. So formal parameter is copied back to it. Now, since I have passed the same actual parameter to both, it depends on in which order this restore is done. If B is copied back first and then A is copied back, then the final result you will see is that of the value of A, which is 6. Whereas if A is copied back first and then B is copied back, the final result that you will see in Z is the value of B, which is 4. So you can see that I deliberately took this example to show you that call by copy restore is not a consistent evaluation strategy. It can very easily lead to ambiguity. And that is the reason it is not considered any further. Right? Finally, let us look at this macro. We have this macro, A into B. And so x plus y, x plus 1, y plus 1. Now it looks like a function, but the difference is, had it been a function, x plus 1 would have been evaluated first, y plus 1 would have been evaluated next, and then those two values would have been passed to the function. In a macro, which is called by name, this whole expression is actually passed. So this becomes x plus 1 star y plus 1, which is basically x plus 1 star y plus 1, which is x plus y plus 1. Certainly it's not doing the intended multiplication. And that is the basic difference to note here, that in call by name, it can actually give you a very different kind of a result. And the fact is that your evaluation of the parameters happen after, at a later point, not before the invocation of the function, which call by valuer will actually do. So this is the laziness of that evaluation. So what you're actually evaluating is x plus y plus 1, which is certainly 4 plus 3, 7 plus 1, 8. So which turns out to be 8. Right? So that is the basic difference that you see between call by value, which is an eager evaluation, and the call by name, which is the lazy evaluation. Right? So with this terminology, let us now,
Sir,
yes, please.
sir, what is the evaluation strategy for Haskell? Because in Haskell, by default, lazy evaluation is being done, but it is, I don't think it is called by name, is it?
See, these are that do not take these evaluation strategy names very strongly by heart in terms of lambda calculus or functional program. This terminology of call by value, call by reference, call by name, these have primarily dominant in the imperative language space, right? So I'm using those from that. So we will see what Haskell does or what the functional programming languages do based on this order of evaluation, which is something between, it could be called by name or it could be called by need, because performance becomes an issue in terms of call by name, because you might as you make it lazy, you might evaluate the same expression multiple times, right? So I think let us go through this order of evaluation discussion, and then we can get back to what we see in Haskell or you know uh, Scheme and those languages, right? It will become obvious as to what they have to do, right? Because in terms of general lambda expressions, the choices become restricted in terms of correctness, right? Is that okay?
Yes, sir.
So let us first define the termination condition for the evaluation. The termination condition is that we'll say that a lambda expression attains a normal form or is in its normal form if it does not contain any beta radix. So, and no delta rule if you're working with a specific domain. So what it means is a lambda expression is its normal form when there is no more function applications are possible, right? So our objective of evaluation is to attain this normal form, right? So you can see that this converges to our usual notion of function evaluation, because if I can reduce a lambda expression, which is the function having applications on other lambda expressions, if I can reduce it to a normal form, and certainly in programming languages, we are working with a domain, so apply the delta rules, what will be left is either a value, which is what we usually get to see in C or C++, or a function, right? What we have not seen in C typically, but in C++, we will see with the use of lambda, what is known as closure objects. So let's deal with the normal form and let us ask 4 questions. This is about the completeness and soundness of our reduction strategy. The first question is, can every lambda expression be reduced to a normal form? If we give you a lambda expression, will you always be able to reduce it to a normal form? That's very important, right? Uh, if you can, if you can reduce the lambda expression to a normal form, can it be done in more than one ways, or there is a unique way? If there is more than one way to reduce, will all these ways of reduction lead to the same normal form, or they will lead to different? And finally, is there a reduction strategy that will guarantee that a normal form expression will be produced? So answers to these 4 questions step by step, and particularly the fourth one, is important to be able to define a programming language based on lambda calculus, the functional programming languages, right? So let's try to answer those. So can every lambda expression be reduced to a normal form? You have seen self-application. So if you do a similar thing, you can see that lambda x xx lambda x dot xx. If you take this expression, then you are applying the first lambda on the second lambda. So the two x's, you obviously need to do, use alpha rule to rename and so on. These two x's, both x's are replaced by this expression. So necessarily you get back the same expression. So no matter how long you do, this will never terminate. So the answer to the first question is no. Every lambda expression is not reducible to a normal form. Okay? Now let's suppose that I have a lambda expression which has a normal form. Right? Not every lambda expression has, but so let's take a lambda expression that has. So this is a lambda expression. Obviously, it is in the applied lambda calculus. I'm using add, mult, 3, 7, 5, all of these domain constants. Now I can do the evaluation in at least two well-defined orders. One is I can do the outermost first. Obviously, it has to come from left because that is the way it is. So I can start by the outermost and then go inside. Or I can start from the innermost and then come outside. Okay? So let's say this is my entire expression, path 1, as I write, path 1 with this expression. Now, if I do outermost, then the first thing I will do is evaluate for this first binder lambda x, which is 7. So I replace 7 in this x. So this is the expression I get. I'm doing outermost. So the next would be to evaluate for this binder y. So I replace y by 5 at 5. Now, I have to do this lambda z. So I do the evaluation for this binder z by 3. So I get mul 7, 3. If I strictly do outermost, then I will have to do add 5. I can do that and say I have a curried version, add 5. And then I have to do mul 7, 3, which is 21. Finally, I do add 5, 21. I get 26. This is the outermost approach. Path 2, approach 2, I could have done innermost. So what is the innermost lambda? The innermost lambda is this, lambda z, right? So I first do that evaluation. Replace binder lambda z by 3. So I get mul. Then the next inner is certainly y. So I do it for y. I put 7. I get, I put 5, not 7, 5. Add 5. I get this. Then I do it for x, which is outermost. I'm coming from inside to out. I get add 5. Simplify delta reductions. I get 26. I can do mix also. Like here, I've done the innermost, that is Z, then I've done the X. I can do the innermost and I mean arbitrarily also, and I also again get 26.
वो लोग का बच्चा वाला ही 1000 लाइन का था.
Okay, so you can see that innermost is basically call by value. Right? That is what you first evaluate the parameters and then come out. Outermost is call by name. Okay? Now, so this says that there is more than one way to reduce a particular lambda expression, as you can see. If there is, the question is, do different reduction strategies lead to the same normal form? Unfortunately, that is not true. So you have this expression. So if I do lambda y first, take this whole expression, apply it lambda y dot 5 on it. Naturally, there is no y in the body of lambda y dot 5. So there's nothing to substitute for y. Right? So when you do try this application, it necessarily becomes 5. Right? I've done the outermost. I do the innermost. If I do inner, I'll first evaluate the parameter. So I'm trying to evaluate the parameter. And we have seen that this does not terminate. So this evaluation means the same. This evaluation means the same, it continues. So we can see that in terms of lambda expressions, it is possible that the order in which you do the reduction, it might reach a normal form or it may not reach a normal form. Okay? So things are getting very murky. First of all, there may not be a normal form. Second, there could be a multiple ways to get to the normal form when it exists. The third is not necessarily for a lambda expression. These multiple reduction strategies will lead to the same normal form. Here we have seen that in one case it leads to a normal form, in the other case it does not. So the fourth question becomes very, very important. Is there a reduction strategy that will guarantee that a normal form expression will be produced? Otherwise you cannot have a language based on it. So the resolution of this question was given by mathematician Curry, who proved that if an expression has a normal form, then it can be found by leftmost reduction. If it does not have a normal form, it does not. But if it has, then that can be found by leftmost reduction. And that is known as normal order reduction. So where we come from the leftmost reduction or the outermost reduction to the inner. And this is the outcome, that it reaches a normal form, which is unique up to alpha conversion, of course. I mean, you can always rename variables, which is unique up to alpha conversion in terms of a normal form. Or it never terminates, as we have seen for the self-application. Now, the question of whether the lambda expression has a normal form or not is an undecidable question, or strictly speaking, partially decidable question, in that if it does have a normal form, then you will get it from normal order reduction. That is the Curry's result. But if it does not have, then it will continue forever. So there's provably there's no algorithmic way to determine for an arbitrary lambda expression as to whether it has a normal form. You are fortunate if it has, it terminates, or it never terminates. Okay? So with this, the whole of lambda reduction has two reduction strategies: normal order, which is the outermost, which is equivalent to call by name, as we have seen, and the other one is applicative order, which is innermost, which is equivalent to call by value. We will continue on this. We are out of time now, so we will continue on this in the next class. Is there any question? No. So we will close here today. Just to remind you that in the next class on Wednesday, we will have the first class test on Moodle. So the Moodle link will be available in the when you start the test. The test would be for about 1 hour. So on Wednesday, initially, we'll have some more discussions on the order of evaluation and close this module. And then we will go ahead and have the test for 1 hour or so. Okay. So the test would naturally be on the second and third module and the initial part of reduction, beta, up to the reduction, not the order of evaluation, of course. Okay, thank you very much. Have a nice day, and we meet on Wednesday again.